Your model can break without a new bug. Evidently, reports show which data changed before you decide to retrain. This is the setup you'll be able to run after this, which compares reference and recent records to detect drift and returns a retraining decision with the changed features. I'm Professor Pi, teaching AI foundations with simple Python. Data drift is a silent failure mode. Your model can get worse because inputs slowly shift, not because a code change broke anything. Evidently helps you spot those shifts early, so you decide whether to retrain or investigate. It is designed to work with tabular data and small classification or regression models, and it scales naturally from toy sets to production streams. At its core, evidential drift reporting compares a reference dataset that represents expected inputs to a current dataset that represents recent traffic. If distributions change for features like age or city, the report flags those features and gives a score. That score is a simple signal you can use to prioritize investigation or gate retraining. We will build a small, concrete workflow. You will see a dataset level check, a single column drill down, a ranked list of changed features, a mapping to ignore an identifier, and finally, a simple retrain decision. Nothing fancy, just clear signals you can act on. Now we will run a simple report. This snippet runs an evidently report with the DataDriftPreset to compare a reference dataset to a current one. It creates simple tabular data with an ID, a numeric age, and a categorical city column, then shifts age and ID in the current data to simulate drift. The report object holds the configured metrics, and the run method executes them over reference and current inputs. The asDict call returns a structured dictionary, and the variable res contains high-level drift results. Finally, the code prints whether dataset drift was detected and the fraction of drifted features. The printed drift status and share tell you if changes are broad enough to merit attention. Next, we will look at one column more closely. This example zooms into a single feature by running evidently's ColumnDriftMetric for the age column. The metric object defines what to evaluate, and the report wraps it for execution. The run function compares the same reference and current data created earlier. The asDict method returns a dictionary with a drift detected flag and a drift score, which represents how strongly the column distribution changed under the chosen statistical test. If you change the feature name, the code analyzes that feature instead. The printed flag and score reveal whether age alone has shifted and by how much. Next, we will rank features by how much they changed. This code ranks columns by drift intensity using evidently results from the earlier DataDriftPreset report. It reads drift by columns from rep asDict, which maps each feature to metrics like drift score. The sorted function orders columns by drift score in descending order, so the most changed feature appears first. The variables name and score capture the top-ranked column and its score, and you can slice the list to inspect more features if you want to prioritize a handful. The printed line identifies which feature shifted the most, helping you prioritize investigation. Now, we will refine which columns we actually care about. This snippet refines the analysis by specifying an evidently column mapping to exclude the ID from drift evaluation and set proper feature types. The ColumnMapping object marks ID as a special column and declares age as numerical and city as categorical, which selects appropriate statistical tests. A new report with DataDriftPreset is run with ColumnMapping set to CM, so the drift computation ignores ID. The R4 variable holds the updated dataset level statistics, after this mapping. The printed drift share WOID shows the fraction of drifted features after removing ID, making the signal more actionable. Finally, we will turn the results into a simple retrain decision. This code converts evidently drift outputs into a practical decision on whether to investigate retraining. It reads the dataset drift flag and the share drifted features from R4, which already excluded ID using column mapping. The variable th is a tunable threshold for what fraction of changed features is considered risky. The flag becomes true if evidently detects dataset level drift, or if the drift share exceeds the threshold. Increasing th makes the gate more conservative. Lowering it makes alerts trigger earlier. The printed decision clearly states whether to look into retraining now and records the policy threshold in use. In a real system, this toy flow maps directly to a daily or hourly check. Feed a stable reference snapshot and the newest batch as current. Log the drift scores and apply the thresholded decision to trigger investigations or automated retrains. The same signals can feed dashboards and incident workflows. Recap. Evidently reports compare reference and current data and score per feature and dataset drift. Use this when you need early detection of input changes before retraining. One caveat. Statistical flags are signals, not proof. Always inspect top features before costly retraining. Next step. Tune the threshold that decides when the share of changed features forces an alert, so it matches your business tolerance for false alarms. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.